Good morning again, and welcome to our webinar, Safety for Autonomous Structures and Field Robots in the Agri-Food Sector. This webinar is part of a webinar series organized by Agrifood TEF, the European Testing and Experimentation Facilities Project, which is funded by the European Commission and member states. My name is Marie Wenzlaff. I am project manager and researcher at Josephinum Research, and I will be moderating this webinar today. At Josephinum Research, located in Austria, we are specializing in close-to-business research and development in the field of digitalization and agriculture, with a strong focus on agriculture technologies, robotics, and AI applications for the agri-tech sector. I am delighted to have my colleague Johannes Zuser with me. Johannes is a robotics engineer and has developed a strong expertise in the field of safety for autonomous machinery in the agriculture context. And in the next 30 to 40 minutes, Johannes will share with us some insights in the topic and showcase some of our recent work in that field. Of course, you have the opportunity to ask questions. Please use the chat or the question and answer tool to send us your questions, and we will answer them after the presentation. And with this, I will hand over to Johannes and wish us all an interesting webinar.
Thank you for the introduction, Marie. Hello also from me, everyone. My name is Johannes Zuser from Josephinum Research. And today we are going to talk about a very specific topic. As the slides say, safety for autonomous tractors and field robots in the agri-food sector. We see a lot of cool videos of robots on the internet and on fairs. They look perfect in the demo. But today we look behind the scenes. We are not just discussing technology, we are discussing liability, certification, and the absolute necessity of safety. Because if a robot hurt someone, it doesn't matter how advanced the AI was. Yeah. Our goal for the next 35 minutes is to outline the path from a working prototype to a market legal product. Here's our plan for the next 35 minutes. We have three main parts. The reality check, we start with the basics. We compare how a human sees the world versus how a machine sees it. We also look at the market and the daily problems in the field, because biology is still far ahead of technology. The rules. This is the most important part. We will talk about the laws, like the machinery regulation and the AI Act. This is the heavy stuff, but I will try to break it down for you so you know exactly what paperwork you need. Then, last but not least, the research spotlight. Finally, I will show you what we are doing at Josephinum Research and within the TEF network to solve these problems practically. Let's start with the reality check. Why aren't our fields full of robots yet? The answer often lies in perception, how the robot understands the world. It is the fundamental difference between data and information. To understand the challenge, look at this comparison. On the left, you see the human eye. But we humans don't just see, we sense. We have an inner ear for balance. We feel vibrations through the seeds. We have a massive processing unit, our brain, that has been trained for millions of years of evolution and in our lifespan, a couple of years and centuries. When a farmer sits on a tractor, he feels if the ground is too soft, he hears if the engine sounds wrong, and he can react intuitively. On the right, we have the machine. It uses cameras, LiDAR, and IMUs. While a sensor itself might be more precise in measuring the exact distance in millimeters or other data, it lacks one crucial thing: context. A machine measures data, A human perceives meaning. A machine sees a value of a distance, and a human sees, okay, there's a danger in this distance. Let's show you what I mean. On the left, you see a picture of the robot Dionysus in a vineyard. For you and me, this is easy. We see the rose, the grass, the sky, and we even see the house in the background. We know immediately this is the drivable area. Now, look at the right side. This is what the machine sees. This is raw LiDAR data. It is just a point cloud of points in the dark. To the robot, a vine leaf and a rock are just obstacles with a geometric shape. It does not know that it can drive through soft leaves, but it has to stop for hard rock. We have to teach it these differences, pixel by pixel. We call this what I talked about, the perception gap. The human advantage is, as we said before, context. If you see a ball rolling on the street, you hit the brakes. Why? Because you know a child might be following. Your brain fills in the missing information based on experience. The machine reality is different. The eye only sees edges and patterns. It does not understand meaning or causality unless we program it for this matter. This creates a big bottleneck, data labeling. To make a robot safe, we need thousands of pictures where we tell the computer, this is a human, this is a crop, this is a stone, this is a danger scenario, and so on. And we need to do this for rain, for dust, for night, and for bright sunlight. The data hunger is huge. Let me give you another example. Think about the Tesla on a highway. It looks for white lines and road signs. The environment is structured. In agriculture, we have an unstructured environment. There are no white lines. The road, in this example, the crops, the vines, changes every day because they grow. It moves in the wind. And what a small plant was yesterday can be a bush today. This implies that agricultural robotics is in many ways harder than automotive autonomous driving because the world is constantly changing. Now look at the robots available on the market. We have three categories. First are retrofit solutions. This means we take an old normal tractor and put a robotic kit on it. The good thing is it is cost effective. You don't need to buy a new machine. It is easily implementable because you know the vehicle and you have it already. But it is hard to make an old tractor perfectly safe for autonomy. The steering often has backlash and the brakes react slower than a digital system expects. Second, the implement carriers. These are new robots, but they work like old tractors. They have a motor and they pull a tool. Pros, you can use your old machines, for example, standard implements, and there is no big structural change needed on the farm logistics. Cons, such robots are pretty expensive and you often need to transport them to the fields with another tractor on a trailer. Third, specialized machines. These are robots built for only one job, like weeding or spraying. They often need structural change. You might need new transport methods or charging stations, but they're often lighter and better for the soul, which is a huge agronomic plus. Now I have prepared some examples of every category we talked before. For example, for retrofit solutions, you can see on the left the AGC autonomic kit, and on the right, a project from A4L with ATI Robotics, where they put a sensor on a standard tractor to make it drive by itself on field and in vineyards. Then implement carriers. We have, for example, the Java KT. It is quite a new robot concept that can use conventional seeding or tilling implements. Then on the right side, you can see the New Holland R4. It looks like a tractor without a cabin. It still has tracks and a hitch to pull standard tools, and it's mainly in use for vine and orchards. Now, specialized machines. I also have two examples for that. On the left, you can see the Kilter iX1. It puts drops of chemical exactly on the weed. On the right side, you can see a drone, the XAG P150. It is a spraying drone. Drones are also autonomous machines in most cases, but we will focus on ground robots. These machines are for very specific use cases and can only be used exactly for these. Now, what are some troubles with that machines? There are many operational challenges you can think of. The biggest problem in the EU right now, I think, is we have a problem that is called the babysitter effect. In the top picture, you can see a illustration produced with Nano Banana Pro. And there you can see, even if the robot is fully autonomous, the farmer has to sit on a chair and watch the robot all day. If one person watches one robot, there's not really an economic gain. Autonomy only pays off if the farmer can do something else or controls 5 robots at once. Then another problem is operability. This is also a big challenge. As we said before, agriculture takes place mainly outdoors. There's dirt, rain, fog, where sensors have troubles. A camera covered in mud is blind. Then third problem. Currently, logistics is a big issue. How to get the robot to the field? How do I refill the spray tank automatically? If the farmer spends 2 hours refilling the robot, the efficiency is also gone. We have to remember, the economic driver here is farmers are not buying robots just for fun. They are facing massive labor shortage because they cannot find people willing to do manual weeding for 10 hours a day. And also the people are very expensive. Now I will show you some success stories. So who is successful in the agricultural robotics and autonomous machines? I have two examples on this slide. The first company is FarmDreed. But why do farmers like them? Because they are simple. They drive slowly, they use a solar power, and they rely on high precision GPS. And the company took a safety wire, so a simple bumper for detecting obstacles. And they do not mainly rely on complex AI sensors. This is better for repairability and lowers the cost of the machines. They show that simple is often better than high tech. Agrifood is also a company that has stepped foot on the market with heavy-duty robots, but for them there are a bunch of problems left regarding integration with implements. But what are these problems, you might ask? One of these problems is a big safety risk we often forget. Look at this diagram. On the left is an example Agibot. You can think of all implement carriers. It is smart and has sensors and is safe. On the right is the implement. It is usually blind, steel, and therefore dangerous. The robot stops if it sees an obstacle in front, but if the tool behind hits someone or something goes wrong with it, the robot often does not know and does not detect problems quickly. We call this the integration gap. We have a blind hazard zone behind the machine, and the robot controls the power of it, for example, with the PTO shaft, but it often cannot see the danger. This is not just a technical problem, it is sort of a liability. If a farmer buys a robot from company A and a harrow from company B, and he bolts them together, it could be thought of in the law that he's a manufacturer of a whole new system, and so he's also responsible for it to be safe. And that is a big problem in agri-tech. We're starting also to see some smart implements, like the carbon robotics laser weeder. It has its own cameras to see weeds, but safety is not the main part of the machine, as safety certification for high power open field lasers is extremely difficult. But most farmers will use standard tools, like the Kuhn harrow. We need to make the shown combination safer so the robot knows what the tool is doing. Now we come to the most important part of my presentation, the rules. How do we make these machines legal? This is the difference between a university project and a product you can sell. We will start with some regulatory context. We have two levels of rules. Firstly, the binding law. These are EU regulations like the Machine Regulation and the AI Act. You must follow these. That is not a choice of yours. You have to follow these. Then we have the so-called soft law. These are standards like ISO. Here's the trick. You don't have to follow ISO standards. But if you do, you get the presumption of conformity. This means the authorities assume your machine is safe. Because if you don't follow these standards, the burden of proof is on you. In case of an accident, you have to prove that your custom solution was just as safe as the standard that is taught in the ISO standards. Most companies don't want to take that legal risk. So you want to make a machine with binding law and soft law. But what do you have to do to make a machine safe in the eyes of the law? This table is a map for safety. And let's look at it closely. On the left side, we have safety for mechanical things. And on the right side, we have security and AI. The first row is the law. We have the machinery regulation, and this replaces the old directive. On the right side, we have the new AI Act and the Cyber Resilience Act. This means cybersecurity is now a law. You cannot sell a robot that is easy to hack. The second row is the fundamental ISOs, like the ISO 12100. It is the base for all risk assessments. On the digital side, we have ISO 27000 for information security management. The third row focuses mainly on control systems. Here it gets specific. For tractors, we use ISO 25119, which also includes an AGPL, Agricultural Performance Level. This is about the reliability of your electronics. On the right, IEC 26434 protects your network from hackers. The fourth row is product specifics. This is also a very important standard for us. On the left side, you can see ISO 1800479. It is specifically for highly automated agri machinery. It defines exactly how the robot must detect obstacles. The message here is you cannot just build a robot, you need to check all these boxes to be compliant. So how do you do this in a project? I tried to give a simplified example for a development pipeline. Step one is definition and ODD. With ODD, I mean operational design domain. You must define where does the robot drive? Day or night, rain or sunshine, outdoors or indoors, and you have to design your robot around that dependencies. If you say daylight only, you don't need night vision, for example. Step two, risk assessment. You look at ISO 12100, you list every possible danger, how critical it can get in each danger scenario, if it's repairable or lethal damage, for example. This is also where the AI Act comes in for high risk components, because most of the agriculture machines are high risk machines in the AI Act. Then step three, design. Now you construct and build the machine around this assessment you did before. You design the safety functions and get sensors and actors for your machines. Step four, testing and validation. This is the hard part. You test the perception with the ISO standard 18479 and the cybersecurity norm and the cybersecurity. Look at the small arrow that goes from step 4 to step 2. It is often the case that tests are failed. So you will have to redesign the concept and do it all over again. That is totally normal. Then, if everything worked, you get to step 5, market approval. Only at the end, you get the CE mark. Remember, this is not always a straight line. It is a repetitive cycle that you do. Let's look deeper at the machine regulation. I have put every law and soft law on its own slide. So you have something to look at and get a little bit of context. The machinery regulation is mandatory for market access. Key point for the agricultural robots here is the autonomy, which can be found in Annex 3. The law says the machine must detect humans and stop automatically. Also, software is now a safety component. If you do a software update over the air that changes how the robot drives, you might need to recertify the whole machine before pushing it to the customer. This is a huge challenge for agile development. Then the AI Act. The AI Act is quite a new regulation, and it focuses on trust and quality. Data validation. You must prove your training data is good. For example, does your dataset include children for outdoor scenarios or people crouching? If not, you have a blind spot and a legal problem. Then a human must always be able to stop the machine. So you need to design a reliable stop override interface. Then you have to integrate a sort of a black box. You need automatic logging. If an accident happens, we need to know why the AI decides to drive. Then there's CRA Act. It's the Cyber Resilience Act. It requires security by design. For example, you cannot use passwords like admin123. And you must provide security updates for the whole life of the robot. To be more precise, for the expected lifespan of it. For example, 10 years. If someone finds a hack, you have 24 hours to report it to the authorities. This requires a completely new IT infrastructure for manufacturers. Because if you need 24/7 security response team and secure servers, and also you need to guarantee updates for 10 years, this regulation raises the market entry barrier significantly. It forces startups and small companies to become professional software companies very quickly. Then for the soft laws, the ISO 12100 is a basis. It tells you to follow the three-step method. At first, you assess all risks of the machine, and then you will do these three steps. Step one is design the risk away. At first, you want to try to make it mechanical. For example, make the robot slower or lighter. If there is any risk left, you need to add guards. For example, LiDAR sensors to detect humans in the near field. And if there is any risk left, you need to do the last step. You add warnings, like stickers or manuals. But what's important to say to this is you cannot just put a sticker on a deadly risk and say, I'm all done. As you can all imagine, that is not allowed. Then ISO 25190. It is for electronics in the agriculture space. We usually need an agri performance level, as I before said, and most of the agricultural machines are put in the category D. This requires a category 3 architecture. This means in safety components that redundancy is needed. You need, for example, two processors which check each other. If one fails, the other the machine has to stop, and that is done over a control system that the two processors control each other. You have to run a safety critical code on a single, not on a single redundant chip. Then ISO 18479. That is the standard for autonomy. It, for example, defines the test bodies. Your robot must detect a dummy that is 700 millimeters high, like a crouching person, and 400 millimeters wide. It also requires mode separation. You need hardware to switch. You need a hardware switch to change between manual, autonomous, and service mode. This ensures that the robot doesn't start driving while a mechanic is working on it. Let's put this all together in a real example. I've tried to make it as general as possible. So now imagine we're building a robot. We will go just through some steps of this slide, but the slides will be published so you can get a closer look on the slides afterwards. I've picked row 3. So now look at row 3, please, which is AI development. You always have some engineering action, as you can see on the top, and some compliance deliverable. For example, at AI development, we can think of an engineering action like we collect 10,000 images for your AI, and we have to make sure that bias is removed of this data. For example, we must include pictures of children, as we before said, and ensure robots also see them. Then the compliance deliverable for AI development. We need a bias analysis report for the AI Act. This is a document you need to show. Now, let's go to row 5. Verification. There you can see the engineering action. We go to the field, and we put the dummy, as we before said, 700 by 400 millimeters into a crop, and the robot should drive towards it at maximum speed. The result in that should be it detects the dummy at around 5 meters and stops really last time is 1 meter before the impact. What you have to for a compliance deliverable, we write a validation report according to the ISO, so ISO 18479. So you can see every step needs engineering, but in the engineering process, you also need a document for compliance. If you don't have the paper, the test for the lawmaker did not really happen. Now we move to the final part. What are we doing about this at Josephinum Research? We are trying to solve this blind spot. So the first project I want to present you is SADA. We are working on this project on anomaly detection, especially for robots. We use different sensors like lidars, cameras, IMUs, or microphones to create a sort of a black box. Because the goal is the robot should know when something is weird or wrong. The purpose is not that it knows exactly what happens. It just needs to know this does not look like a normal field. I should do something. And this is not normal behavior. There's more vibration than normal. I should do something. We test these things on the farm grid, as you can see on the left, and on our own engineered robot on the right, the Dionysus, in ginkgo plants. The second project I want to show is smart agri systems. We before looked at the so-called dump implements. For example, we use a cultivator and a till harrow. In this project, we analyze the CAN data of the tractor and add sensors like accelerometers and also microphones to the tool. And with this data, we want to detect if the tool hits a stone or gets blocked or any other anomalies or dangers. We want to make the whole machine smarter, closing the integration gap I mentioned earlier. Then a special project of us is also AI5. In this, we built a prototype for the Spanish riding school in Vienna. It is an indoor robot to fix the sand in the arena, even though the robot is indoors, safety is also crucial in that scenario because there are high value horses in this area and also working people and riding people around it. That's a use case I find interesting because you can see it can be used in many niches, but the safety principles remain the same. So now I've talked about a bunch of stuff like humans as a difference between human T and humans have context, to machines that only get data and you have to train them, and the laws, and at the end, the projects we do at Josephinum Research. But what is the bottom line of all of this? If you remember three things from today, I want it to be these. First, context is king. We see the perception gap. So a machine sees raw data and a human sees meaning. To make robots safe, we must teach them to understand the context of the field, not just detect obstacles. Then the second thing is safety meets security. With the new regulations like the AI Act and the Cyber Resilience Act, the game has sort of changed. You cannot have a safe machine anymore without it being secure against cyber attacks, because autonomous machines that can be hacked are pretty dangerous, especially for agricultural machines that are mostly heavy and can do much harm. The third thing is don't guess, validate. That's why TEF is an important project, because the only way to bridge the gap between a prototype and a product is rigorous testing. You need to go to the field, use the standard test bodies, and prove your safety concept in real world. So my last sentence will be safety is not a feature you add at the end. It is our license to operate. So I will thank you for your attention and will let Marie take the word over.
Thank you, Johannes. Thank you for this comprehensive overview. And I want to conclude this presentation of the webinar with making the bridge towards the Agrifood TEF project that you have highlighted just in your last sentence. And could you please go to the next slide, Johannes? Thank you. Yeah, as partner of the Agrifood TEF project, we can contribute our expertise in robotics and safety to help companies further develop their robot prototypes tailored to your actual needs with customized services and without complex paperwork. With the Agrifood funding opportunities, we are very flexible in providing testing and validation support to accelerate the market readiness of your solutions. And startups and SMEs in particular from all across Europe can benefit from Agrifood TEF funding and receive technical support from us and our partners at highly reduced costs. Well, and with this, we are at the end of our presentation part for this webinar, and we'll now open the floor to answer your questions. And I have already seen there are a couple in the chat, so I will go from top, starting with from Simon. There is a comment that ISO 18497 is a type B. It's more a statement. Johannes, would you like to comment on that or clarify anything?
Yeah, that is totally true. It does give some differences in standards. There are harmonized standards, there are type A standards, there are type B standards, there are type C standards, and I also think ISO 18479 is a type B. If I put it wrong in the presentation, I am sorry.
Thank you. So, next question. Can you explain why you are of the opinion that ag robots are high risk under the AI Act? And in brackets is the comment added, is AI used as safety component?
Yeah, I have talked about this with some experts of the Johannes Kepler Universität in Linz, Austria, that have very much expertise in these matters. And as I understood these conversations, there are some conditions that machine is labeled as high risk in the I Act. And if I think of it correctly, it is that for agricultural, I can really grab it what I want to say. Because most machines in the agricultural sector fall under the machine regulatory, It is, I think, automatically triggered that is under high risk classification. So I think all machines that have are put under the machine regulation are under the High Risk AI Act, if I say that correctly. But I will look into it later and give an opinion. You can write an email to me as well. Oh, sorry. So here.
Thank you, Johannes. I think this question was answered quite good and comprehensive. And yes, like you said, if there are any more needs for clarification, then you are always welcome to send us email requests. So next question, for which purposes or functions AI is used in autonomous robots?
Um, you have, for example, if we think about the Agrifood or any other robot in the agricultural space, uh, you have vision on it. This is like cameras or lidars or so it is for localization, mapping, and navigation. So you mostly need sensors like cameras and lidars and their data for obstacle detection and navigation. So it's a crucial part of most of the autonomous robots in the agricultural space. So you have AI nearly in everything.
All right, thank you. Next question or comment. Let me go over this. I believe that to obtain presumption of conformity to the machine regulation, standards have to be harmonized and cited in the European official journal. So this is an add-on comment to the discussion we had before. Thank you for that, Simon.
Mhm.
Let's go to the next question. Yeah, in automotive, the notion automation is used and not autonomous. In robots, autonomous is used. Why is this distinction made?
I don't really know why it's called autonomous because the lawmaker don't really like it as I have experienced. It is quite a, a, a big word that is autonomous, and I would personally not label my robot as autonomous. Uh, Better is automated robot, as you also said, because lawmakers don't really like autonomous. But I don't really know why it's called autonomous in agrobots. It's just the usual slang in agriculture.
Thank you. We have two more questions to go at the moment. There's a thank you from Nicholas. And the question, is there already test methods available to validate AI-based safety systems as described in the new machine regulations? Do you know anything about this, Johannes?
I I don't really know about the AI components, but if you talk about sensors and all of it, you can take a look in the ISO 18479. There it is talked about what verification methods are needed. For example, what are the operation zones and what are edge cases, and you can test on basis of this ISO, so 1800, also 18479.
Thank you. Another comment. I think that is only the case when the AI is used as a safety component. Yes, and that was exactly the point that you made, Johannes.
Mhm.
That's why I was wondering. I will email you. Okay, perfect. Let's take this to a deeper conversation outside of this. Thank you. Thank you all for your active participation. There is again another question in the chat just right now from Miriam. Will you be able to close the integration gap by making use of isobus for automated functions and safety?
Um, I think so. Yeah. Because then you have a good, simple communication tool, and which is a certified ISO, which all tractor manufacturers and implement manufacturers could talk the same language. So you could bridge this safety gap with a good implementation of isobus. I think so, yeah.
Thank you. Thank you all. Thank you for your time and thank you for your participation. We have another comment, I would say, in the question and answer tool that clarifying that high-risk AI is only for safety functions. That is clear so far, and there is, however, a distinction between self-evolving and fixed systems. So we have a really specialist here in the audience. Thank you for all your input and engaging with your questions and comments. With this, I think we are at the end of the webinar. I'd like to thank you, Johannes, especially for this insightful overview on the theoretical background, as well as showcasing this topic and how it is tackled with various different research and innovation projects at our institute. Dear listeners, we'd like to thank you for your interest and time. If you have any more questions or would like to explore collaboration opportunities with us, do not hesitate and contact us. If you are interested in discovering more online materials and learning more on robotics, AI, or related fields, we have some resources produced and will keep on producing webinars and other information materials throughout the Agrifood Dev project period. And you will find them online on our homepage, on our website, agrifooddev.eu. Please check out especially the training section where we upload the webinars and also the event site for other webinars apart from technical trainings. So thank you so much. And of course, yes, like said in the chat from my colleague Rita, we will make available the presentation as well as the recording afterwards. Thank you so much and wish you a good day.